So now I'm going to show you even more calculator tricks. When you could see from the graph that this equation that we're looking at had actually two x-intercepts, and we only found one of them. We found the one that was close to 1, and we found it to be 1.164035 to 6 decimal places. Okay, now we're going to look for the other one that's near x equals negative 1.5. So in our seed value for the iterative process, we're going to use x is approximately equal to negative 1.5. All right, now here's the super trick that we're going to use on the calculator now. And I keep having to go, this number minus this number divided by that number. And I know that this number was y1 and this number was y2. Well, maybe I could set up a y3 that does that. So my y3 is going to be this. It's going to be x minus. So the cool thing is that within one y variable, you can call on other y variables. This is variable y-varis function y1. I do have to put in that it's evaluated at the point x, and then divided by variables y-variables function y2, all right, and that's also of x. So once I put that in there, all right, then the cool thing is all I have to do is go back here, and my first x value is negative 1.5. That's what I'm going to use, right? That's my first one. So now I have tuna fish on my calculator. That's not cool. All right, I have cats look at my calculator. So what I do then is I do variables, y3, and the y3 is going to call in all the other variables that I need. So then y3 of, and I just use my starting value, negative 1.5, enter, and I get an error. That's so nice. Let's go to it. So when I put the go to, so whenever it says quit or go to, pick the go to because it tells you what you did. I put the wrong minus sign. It's supposed to be the little minus sign. All right, I get negative 1.455. All right, negative 1.455. That's my second variable. All right, yeah, let me take a moment to appreciate the fact that this requires that you have the function in y1 and the derivative in y2, and then you can set this up. All right, and now I can just say, all right, let's do y3. I mean, really, you could copy and paste, but it's probably easier to just go to y3. Don't forget the parentheses, my most common error, of this number, close parentheses, enter. And it gives me negative 1.45263. All right, so my 3. I'm going to keep 6 decimal places again, 452,633, because we're still shooting for this, 6 decimal places of accuracy. So I'll just keep going until the 6 decimals don't change. All right, so when n equals 4, I'm going to go variables, y variables function, y3, parentheses, this is my x3 right there already, and enter that in, and then I can just enter again. Now I've got 4526, so negative 1.452627. We can see that we've already got 1, 2, 3, 4 places of accuracy after 4 iterations. So this is a method that converges rapidly and gives you high degrees of accuracy. And of course, we could do 50 iterations, and get with a computer, have a computer do it. You guys who are in you guys who are in AP Comp Sci, all these numerical methods that we do, you should try writing programs for them. See if Mr. Savoysky or somebody will give you extra credit. Anyway, variables, y3, that kind of level of you can program this computer. This calculator. It's programmable. I bet you could find a way to program in these steps so you didn't even have to type this, and it could just spit out the first, however many iterations you want. Negative 1.45262. Yeah, 7. It's 7, but I'm rounding because this one was. Wait, did I get that? 452,627. Because this one was 6, 8, 4, 5, 2, 627. Oh, 6879. Okay, they are the same. All right, I don't know why I was thrown by that. But our x5 is equal to our x4 to 6 decimal places. Of course, they differ perhaps at the 30th decimal place. We'll never know. So we can take this as a good answer, and you can see how quickly we get to it. You could program something to do that very quickly. All right, so very nice.